Hi everybody, welcome back to the Feynman technique. So today we are going to be using the same process we've been using to develop a closed form expression for this integral in terms of a and b. All right, so the first thing to do is we're just going to call this a function of a, and our b is going to be an arbitrary constant, and we will assume that b is greater than 0. All right. So before we do the technical first step, which is to differentiate under the integral sign, let's check for values we know. So at a is equal to 0, our original integral becomes this, and it evaluates to 0. All right, so we know f of 0 is equal to 0. So we jot that down over here. All right, now let's take the derivative of our function of a using the Leibniz rule for differentiation under the integral sign, which says that we can take the derivative directly by passing the derivative inside the integral sign. So if we pass this derivative with respect to a inside the integral sign, it becomes a partial. And then when we take the partial, this is what we get, which simplifies to this. So now this is an integral that we already know the formula for, but we're going to derive it again. We derived the formula for this one in the last video, but we're going to do it again. All right. So now, oh, I forgot. Oh, never mind. Okay. So now we still have an x in the denominator, so we need to get rid of that x. So let's take another derivative with respect to a. And if you do that, we'll finally get rid of our last x in the denominator. And now we just have this. And that can be evaluated using integration by parts. And if you evaluate that using integration by parts, you find that it's equal to b over a squared plus b squared. So this is our f double prime of a. So we started with this, and now we have a closed form expression for its second derivative. All right. So let's go back to f prime of a by integrating our second derivative. Again, integrating this is fairly standard. It evaluates to arctangent a over b plus a constant of integration. Now we can solve for that constant of integration by letting a equal 0. If we let a equal 0 in our original f prime of a, we find that f prime of 0 is 0. If we plug in 0 for this a right here, we get sine 0. So it equals 0. All right, therefore the entire integral equals 0, and therefore we have c1 is equal to 0. If we use the condition f prime at 0 equals 0, we have 0 is equal to arctangent of 0, which is 0 plus c1. c1 is equal to 0. Therefore, we have our closed form expression for f prime of a. So we integrate one more time to get back to our original f of a, and that's our answer. So integrating one more time, now we have to integrate this. That's not so easy. You can do it like this. Here's the hint: is u is equal to arctangent a over b, and dv is equal to dA. So you're going to use integration by parts on that, and you should arrive at this. Again, that's standard calculus 1 techniques. You would learn that in I believe a lot of people would learn that in high school in calculus BC. All right, so here is, we almost have f of a. Now we just need to use the fact that f of 0 is equal to 0 to find our constant of integration. So f of 0 is equal to 0 implies that negative b over 2 natural log b squared plus c is equal to 0, which means that c2 is equal to b natural log b. And we finally have our closed form expression for our original integral that we started with. And this is it right there. All right, guys, I hope you enjoyed that, and we'll see you next time.